All right, so in this video, we're going to go over some more transformations of graphs. We're going to go over vertical compressions or stretches, and we're going to go over horizontal compressions or stretches, okay? So with vertical compressions or stretches, what we're doing is we're taking a function like f of x equals x squared, and we're going to multiply that entire function by some coefficient a, okay? When that happens, okay, the graph of the new function, okay, is going to be obtained by multiplying each y-coordinate from the original function, okay, on the graph of y equals f of x by that coefficient a, okay? So we're going to save horizontal for a little bit later. So right now we're going to go over part A here. We're going to multiply this function by a coefficient of 1/2, okay? So let's look at the original function first, just a quick table of values. When you plug in these 5 values for x, you get these 5 values for y, okay? And we're going to do vertical compressions or stretches here. We're going to see what happens when we've got a fractional coefficient like 1/2 and when we've got a constant coefficient that's greater than 1 here, like 3, okay? But we're going to do part A first, okay? All right, so when I multiply by 1/2 here, my original x coordinates are going to stay the same. So the first x coordinate I'm going to deal with is -2, okay? Now, obviously, you can kind of plug this in and see what you get, but we want to get to where we understand how these compressions or stretches come about. So when I plug in -2, I'm going to multiply this y-coordinate by that coefficient 1/2, okay? And it makes my new y-coordinate for the x-coordinate -2 equal to +2, okay? When I try a -1, okay, remember -1 corresponds with a y-coordinate of 1. I'm going to multiply that by 1/2, and I get +1/2 there for that y-coordinate, okay? When I plug in 0, okay, 0 times 1/2 gives me 0 again for my y-coordinate, so that stays the same. That's going to be the vertex of this parabola here. X-coordinate of 1 corresponding with a y-coordinate of 1. Now it's going to correspond with a y-coordinate of 1/2 because we're taking 1/2 of all the y-coordinates. So 2 is going to correspond with 2, okay? So you can see how the x-coordinates stayed the same, and all we've done is we've halved, okay? We've multiplied all the y-coordinates by that coefficient of 1/2, okay? Now let's look at part B. Instead of our coefficient of f of x being a fraction between 0 and 1, we're going to make it a number greater than 1, in this case 3, okay? So again, the x-coordinates are all going to stay the same. We're going to use -2, -1, 0, 1, and 2 for my x-coordinates. And I'm going to go back. Remember, I'm going back to the original function, not this transformed function from the first part, okay? I'm going to multiply my y-coordinates now by that coefficient 3, which is my a value, okay? So -2 corresponded with 4 before, now it corresponds with 12, okay? -1 corresponded with 1, okay? Now it's going to correspond with 1 times 3, which is 3. 0 corresponded with 0, now it's going to still do that because that's my vertex. We haven't done anything differently there. If you'll think to our vertical shifts and horizontal shifts from earlier in this unit, that should make sense. Our x-coordinate of 1 is now going to correspond with a y-coordinate of 3, and our x-coordinate of 2 is going to correspond with 12, just like -2 did, okay? Now let's take a look at the graphs and see, when we have this coefficient of the function, what it looks like visually. All right, so let's go to Desmos here and take a look at these graphs. Again, we'll start out with the original function y equals x squared. Okay, and you can see we've got a basic parabola here with a vertex at the origin. We've got -1, 1 here, -2, 4 here, +1, 1 there, and then 2, 4 there, okay? With our first transformation, y equals 1/2 x squared, okay, what you see is we've got kind of what we call a vertical compression, or we're shrinking the graph. We're taking this original graph in red and we're kind of shrinking it down, okay, or compressing it. And what it does is it kind of flattens out that graph a little bit, and that creates this blue function, okay? Still has the same vertex, but all the other y coordinates have gotten smaller, okay? An x coordinate of -2 now has a y-coordinate of positive 2 instead of the 4 like it was before. So we're shrinking those y-coordinates if you want to think about it like that, okay? With our second transformation here, y equals 3x squared, okay? It's the green graph here, and you can see we're kind of taking this red graph and we're kind of stretching it. We're kind of pulling at it. If you'll think of it like strings, we're pulling it upward, okay? And what happens there is each y-coordinate, notice for any x-coordinate, like 1 here, our y-coordinate has gotten a lot bigger. We've stretched it out, okay? And that's because we're multiplying each of those y-coordinates by a number greater than 1, okay? So the blue graph would be considered a compression or shrinking of the original function, and the green graph here would be considered a stretching of the original function, okay? So that's vertical compressions or stretches, okay? Now let's look at horizontal compressions and stretches. Okay, so now we're looking at horizontal compressions or stretches of graphs. So notice up here we were multiplying f of x times a coefficient a, and we used 1/2 and 3 in our examples. Here we're multiplying the argument x by a coefficient, and then we'll be doing whatever the function asks us to do. We're going to continue working with this quadratic f of x equals x squared. Now we're not just going to be squaring the x, we're going to be squaring something times the x. And you can see the difference, hopefully, between this version and this version, okay? What's going to happen here, the y-coordinates are going to stay the same from the basic table of values that we use. What's going to change is the x-coordinates, okay? The x-coordinates are going to be multiplied by a factor of 1 over a, okay? Whatever this coefficient is right here, we're going to take the reciprocal of that, and we're going to multiply the x-coordinates by that reciprocal, okay? So for this, we're going to have f of 2x for our first example, and then f of 1/2 x for our second example, okay? So just like before, we've got our basic table of values here for our parent function, this quadratic, all right? So we're dealing with horizontal compressions or stretches. So I'm going to replace x in this function with 2 times x, okay? So notice we're not just squaring the x this time, we're squaring whatever 2 times x is, okay? So remember, we're going to multiply the x-coordinate from our original function times the reciprocal of that a value. So we're going to be multiplying by 1 over 2, all right? So in my original table of values, I had -2 as my x-coordinate. I'm going to cut that in half, -2 times 1/2, which gives me -1, okay? But my y-coordinates are all going to stay the same. So -1 corresponds with 4. Like I said before, you could always just plug in -1 and evaluate the function, making a table of values the regular way. But we kind of want to understand these compressions, these stretches, for functions that are a little more difficult, okay? So my second x-coordinate, I'm going to take half of that. So my new x-coordinate for that point will be -1/2, but it's still going to correspond with that y-coordinate 1, okay? Continue taking half of the x-coordinates, but the y-coordinates are going to stay the same. So 0 will still correspond with 0, and so on. 1 times 1/2 is 1/2. Y-coordinate will be +1, and 2 times 1/2 is 1, which will correspond with 4, okay? And finally, let's go over D here. So we're going to graph the transformation f of 1/2 x. So notice we're multiplying the argument times 1/2, okay? So we're multiplying by 1 over that 1/2. Well, 1 divided by 1/2 is 2. So I'm going to be doubling all these x-coordinates while all these y-coordinates stay the same, okay? So double that -2, and that will be my new ordered pair for this transformation. Double the -1, okay? So -2 now will correspond with +1. Double the 0, which still gives me 0. My vertex isn't changing in any of these, you'll notice. I'm going to double the 1, which will still correspond with a y-coordinate of 1. And I'm going to double the 2, which will still correspond with a y-coordinate of 4. Okay? So let's go to the graphs and just kind of see visually how these transformations are going to look. Okay, so just like before, I've got my basic function here, y equals x squared. Remember, we're talking about horizontal stretches and compressions here. So my first transformation with the horizontal stretch or compression was y equals 2x to the second power. So notice what's happening here. We're kind of compressing this. We're taking this original function in red and we're compressing it in. We're shrinking it, so to speak, by making all the x coordinates smaller. We're moving in towards that vertex. So that would be considered a shrinking or a compression. So anytime you've got a value here multiplied by that argument x that's greater than 1, it's going to be a shrinking, a horizontal shrinking again of that graph, okay? All right, if we've got a number between 0 and 1, okay, notice we're taking that original function in red and we're kind of pulling it apart. That's a horizontal stretching anytime you've got this 0.5, okay, between 0 and 1 times the argument x, okay? So notice how the different values work either with the vertical stretch or compression or with the horizontal stretch or compression. What I suggest is playing around with different kinds of functions. I'm not going to go over these, all the different example problems in the notes, but use cubic functions, do the same thing, see what happens with the graphs. Use quartic functions, 4th degree, 5th degree, and so on, okay? And you'll notice that these things continue to happen. It's all based on what we're multiplying either the x by or the entire function by, like we did in the vertical compressions and stretches.